Vectors and matrices are used a lot in engineering problems. It's a good way to contain a lot of information and solve for multiple things simultaneously. So for us to understand what a matrix is, we first need to understand what a vector is. So that's what we're going to take a look at in this video. When we look at a vector, we define a vector as a vector when we know a direction and a magnitude. Magnitude just means a given value to represent it. So a force can be made as a vector, right? Your weight is a good representation of a force that's defined as a vector. There is direction. The direction is in a downward force, in the downward direction due to gravity. The magnitude will be the numerical value of it, right? So your weight is a good representation. I can push against a wall. How hard I push against the wall, that's the magnitude. In which angle I push, do I push directly on it? Do I push at a upwards angle? That would be the direction component. Velocity and speed is a good way to distinguish a vector from a scalar. So speed is considered a scalar. It just has a magnitude or a numerical value associated with it. This cart is going at 5 miles an hour. If I say this cart is going 5 miles an hour towards that tree, I give it direction. Or if I say in a northwest direction, that gives it direction. That makes it a vector at that point. So we draw a vector just as a line with an arrowhead. The arrowhead represents the direction of this vector. The length of this vector is defined as your magnitude. We define the name of the vector with either bold and like a variable that's bold, or with an arrowhead, or both. So the right arrow above it is useful if you're handwriting and you can't make something easily identifiable as bold. In text, if you're typing, it's easy to make something bold, but sometimes textbooks will show with both, right? So any combination of it defines this as a vector, named vector. Now, like I said, the magnitude is just the length of this vector. Now, when I say length, I put this in quotes because it's a bit arbitrary. I get to define, is this length in units of newtons, like in force, or is it in units of meters per second? And then what defines a unit? Is this whole length 5 meters per second? Is half of it 5 meters per second? So I need to put some context to it. But the length does not need to be in like meters or inches. It doesn't need to be in a length scale. It could be any other property that you can measure a value for, where direction makes sense. For example, you wouldn't make a vector of temperature. That doesn't make sense. But you can make a vector of temperature gradient. The temperature is changing in this direction by this amount. That's something that you could make a vector for. So when we measure or calculate the magnitude, now this becomes a scalar. This is our representation of a magnitude. We write the variable for the vector, the v, and then we draw two vertical lines on both the left and right side of it, and this tells me that I'm measuring the magnitude. It has no directional component. It is just the length in whatever units my vector property is in. The direction could be in x, y, and z direction. Now, for classes and for the sake of simplicity, in these videos, we're going to look at x and y only. But in the real world, you have x, y, and z. And so you take your vector and you place it somewhere along the coordinate system, your x, y, z coordinate system. Now, in actuality, it doesn't matter where you place it. The length of this vector doesn't change if you move it over here or over here. The direction of your magnitude doesn't change where you put it as well. It is the same direction. The relationship between the base of the vector and the end of the arrowhead defines the vector, not the placement within the coordinate system. The coordinate system helps define the unit components that define your magnitude piece. So if I want to break down this vector into its components, let's say it has x, y, z components, I can write it as vx, vy, vz. Now, each of these terms is just a number. Combined together, it makes a vector, because combined together, it gives it a reference to each other as a giving it direction. We can also write this vector in terms of basis vectors. So we'll talk more about basis vectors a little bit later in this video, and we'll talk about it much more in future videos. So these vectors are basically useful representations of direction. They are 1, 0, 0, 0, 1, 0, 0, 0, 1. So it's all zeros except for one direction. And so that makes it basically like, these are what we call unit vectors. They have a magnitude of 1, and they're pointing in only one direction, either x, y, or z, in the positive x, y, or z. And we represent them as I hats, j hat, and k hat. They're called I hat, j hat, and k hat as well. So it's basically the I, j, or k lowercase value in bold, and on top of it, instead of an arrow, we draw a little hat, which is basically like a carrot top, right? So like a reverse letter V. And so that's just the standard notation for these. And so because this is basically the x direction, the y direction, and the z direction, we can rewrite this vector as Vx times I hat plus Vy times j hat plus Vz times k hat. I, j, and k are vectors. Vx, Vy, and Vz are scalars. So what is a scalar? Scalar is just a number without a direction. So the magnitude is a scalar. If I say any of these values without giving it direction, those are scalars. If I say Vx, Vy, or Vz, because I don't give it direction, those are also scalars. So understanding the difference between a vector and a scalar is extremely important. And as you solve your problems, making sure that you clearly denote what you're writing. Are you writing a vector or a scalar? Because how you use a vector or scalar is very, very different as well. How do we find the magnitude of a vector if we know Vx, Vy, and Vz? Well, what we do is basically solve for Pythagorean theorem, right? So yes, this is 3 components instead of 2 that you're probably used to, right? You're probably seeing a squared plus b squared equals c squared. A vector is essentially a triangle, right? I can draw the multiple components of it. So let's say this is a 3-dimensional vector. You can draw a right triangle where the base falls on the xy plane. And then you could draw a secondary triangle where it's just the Vx and Vy components. So if you go Vx squared plus Vy squared, just take the square root of that, that would be the base of my first triangle. Then you take the square of that, then it's just Vx squared plus Vy squared. And you add it to your third leg, which is your Vz term. So then it'll be Vz squared. And square root of all that will be the length of your vector, right? Or that last triangle, that first triangle. So this is just Pythagorean theorem. It will be easier for us to work with a 2D space. So if there is no z component, then this will just be Vx, Vy, or Vx I hat plus Vy j hat. And in this case, the magnitude is just square root of Vx squared plus Vy squared. It is exactly the Pythagorean theorem. Okay, so I want you to try to solve for the magnitude of these 3 problems. We have a hat, b hat, and c hat, and I give you the x and y components of each of these. So hit pause and use this equation and see if you can solve for the magnitude of each of these. When you write out the magnitude, write it as 2 vertical lines, a with the right arrow above it, and two vertical lines on the right of it. Right, so just get used to the notation. Okay, so if you've try to solve these. These are fairly straightforward ones. So first I want to show you the graphical form of these. So this one right here has an x component of 3. And I'm going to place this anywhere. So I want to demonstrate this. So this base here to this arrow has 1, 2, 3 x components if you project the x piece. And then the y component is 4. So from here, 1, 2, 3, 4. So I can place it here, and I give it it's the correct length and it's the correct direction. I can also move this arrow to have the origin as its base, and it's the exact same vector. I have not changed the definition of this vector at all. So I can move this around as long as I don't rotate it, and as long as I don't change the length of it. I'm looking at the same vector. So here are the 3 vectors. There's 3, 4. This is 0, 2, and this is 1, negative 1. And these are the magnitudes of each of these. So we'll walk through them. So a hat is the magnitude of a is equal to square root of the x component squared plus the y component squared. So 3 squared plus 4 squared. Square root of 9 plus 16 is square root of 25, which is 5. The magnitude of the b vector is, this one's easy because you have one direction that's 0. If that's the case, and there's only it's only two-dimensional, then the other one is the magnitude, right? And we can see that here. Square root of 0 squared plus 2 squared is just going to be 2. And then lastly, this is 1, negative 1. Square root of 1 squared plus quantity negative 1 squared is equal to square root of 1 plus 1 or square root of 2. Right? So finding the magnitude is fairly easy, but it's very important, and we use this a lot to compare forces, but direction's also very important too. So last thing for this video, just the introduction to vectors that I want to introduce, is the unit vector. We've seen a unit vector already. This is when I introduced the basis vectors, the I hat, j hat, and k hat. So these vectors have a magnitude of 1. That's the only definition of a unit vector. But you can find unit vectors of existing vectors. And in those cases, we do force the magnitude to be equal to 1, just like the basis vectors. But instead of just pointing in the x direction, y direction, or z direction, we make it point in the direction of an original vector. So we give you a vector, and you want the unit vector of that original vector. So all you need to do is force the magnitude to be equal to 1, but you want to keep the same relationship between x, y, and z, right? So I can scale my my vector up or down depending if its magnitude is currently above or below 1. But I can keep the relationship between x, y, and z consistent so that the direction is still the same. So the way to solve for it, if I call u my unit vector and v my original vector, I just take the original vector and divide it by that magnitude. This forces this vector to be have a magnitude of 1, right? This unit vector should have a magnitude of 1. This also, because we're just dividing it by a scalar, this forces the relationship between the x, y, and z components of this vector, original vector, to remain true with u. So we looked at these 3 vectors in the previous example when we're trying to solve for the magnitude. So let's use these again. And let's solve for the unit vector of each of these. So I have not introduced how to divide or multiply a scalar with a vector. I'll introduce it slightly here, and we'll have more detail about it in future videos. But essentially what you do is, if you're dividing this vector by a scalar, you manipulate, or you divide each term by that same scalar. Okay, so I give you each of these. So just for ease, a hat, little a hat I represent the unit vector as capital A hat, capital B hat, capital C hat, and so forth. Just this is not convention. This is just for the ease of this video. All right, so let's focus on not A, did I say A hat, B hat, C hat? No, the A vector, capital A vector, capital B vector, capital Z vector is what I meant. Okay, so we take the vector and we divide it by the magnitude. So for A, I have 3, 4, and I want to divide this by my magnitude, which is 5. So times 1/5. So I take that first AX term and divide that by 5, so 3/5. This second, the Y component of it, 4, and just divide by 5, so 4/5. It's literally that straightforward, right? So 3 divided by 5, and then 4 divided by 5. And just to prove out that you do get a magnitude of 1, we can take the magnitude of this unit vector, right? So it's the square root of this term squared plus this term squared. So 3/5 squared plus 4/5 squared, right? Just like we did in the previous slide. So this is equal to the square root of 3 squared, 9, divided by 5 squared, 25, plus 4 squared, 16, divided by 5 squared, 25. So this is square root of 25 over 25, which is equal to 1, right? So this will always be true. It's just the nature of how the magnitude works, and that you're specifically dividing by the magnitude of the vector. For the B vector, this was 0, 2. So we remember from the graph, it was pointing in the positive y direction. So this would just be j hat essentially. But we can write it out, right? So the B vector is 0, 2, and we divide it by the magnitude of the scalar 2. So 0 divided by 2 is just 0, 2 divided by 2 is 1. And you could solve for the magnitude, and you would see that this equals 1 as well. For the C vector, we have 1, negative 1, and the magnitude is square root 2. So we divide this by square root 2. So we got 1 over square root 2, negative 1 over square root 2. If we multiply by square root 2 over square root 2, sometimes a cleaner form will be square root 2 over 2 and negative square root 2 over 2. Right? So a unit vector is nice because it tells you the direction of your vector without telling you the magnitude. The magnitude is nice because it tells you the length of that vector without telling you the direction. So basically, the unit vector breaks apart one piece of the vector, and the magnitude breaks apart the other piece. Combined, they are the full vector. Now, there are reasons why you want to split them apart. You want to compare certain things and between different vectors in just looking at the magnitudes or just looking at the direction. That would be a way to do it. So the next video, we'll take a look at what is a matrix. So we'll look at multiple vectors, and future videos we'll look at different vector arithmetic and how vectors and matrices interact with each other.